So good morning, everyone. We are Colchester Royal Grammar School from the UK. I'm Dia. I'm in year 13 or grade 12.
I'm Calvin. I'm also in the same year as Dia, and we're actually in the same class as well.
Same with me, I'm Stan. I'm also year 13 and in their class as well.
Hi, I'm Jula, and I'm also in year 13.
Okay, so welcome to our presentation. So first of all, we'll talk about what technical computing actually meant to us. This was turning theory to a real-life impact, using abstraction, of course, to turn a big problem into mathematical layers. This problem, of course, was not just one equation. We had 3 scales: household affordability, behavioral gambling dynamics, and then a long-run recovery model. So we kind of have an ideological pipeline from affordability to escalation and then to the recovery burden. So in terms of how the models connect, question 1 identifies the vulnerability before the gambling begins. Question 2 models how behavior converts vulnerability into the losses itself. And then question 3 measures how long the damage lasts after the betting stops. So I'll introduce question 1. First of all, this is about modeling a person's disposable income. We use salary and demographics. We test how vulnerable it is to the unexpected emergency costs by implementing a 2-part model: a deterministic layer, the predictable costs, and then the stochastic layer, which are the unpredictable costs. Mathematically, this is a discrete time stochastic model, or more precisely, a compound Poisson shock model embedded in a deterministic monthly cash flow equation. Just to kind of briefly summarize what this is before we go into detail, we sum the net income, subtract the essential costs, and then subtract the emergency costs.
So the data we used for this question are for tax, the official state and government websites. For cost of living factors, we decided to use house, food, transport, and healthcare costs. And we used the provided ONS data for the UK and the MIT living wage calculator for major US states. Then we used this data in Excel spreadsheets and passed it into CSV files using Python scripts. And we also took data from research journals for estimating the frequency and intensity of unforeseen essential spending. And here are example CSVs we used for tax rates and essential costs.
So our model starts off by defining multiple personas with different demographics over which we test it. And for each persona, we convert their annual net salary, their annual gross salary, into a monthly net salary because our model works on a month-by-month basis. Then we calculate the fixed costs, which are split into multiple components, which are derived from the table on the left. And we also include variable costs, which change on a monthly basis using a cosine curve stretched across the span of an entire year. And then we add the variable costs to the fixed costs and scale them according to a scale factor determined by the OECD, which adjusts for household structure for the persona. And combining with the deterministic part of our model, we also include a Monte Carlo simulation, where we use a Poisson distribution to identify the number of shocks, financial shocks per month, and a log normal distribution to assign a severity to each shock. And then we run multiple simulations and average the results to get the total financial shock for a single month. And then we combine all of these costs and deduct them from the monthly income and summate over 12 months to obtain the final yearly disposable income. And here is a summary of our pipeline.
So what our model showed, our first insight is that lower income persons in the US spend a much higher proportion of their income on essentials compared to other demographics. Another conclusion is the inequality between the UK and the US. Firstly, the proportion of income spent on essentials of a high-income single person in the US is greater than that of a base UK family. Secondly, the probability of a base UK family of going into debt is 9 times lower than that of their US counterpart in a given month. Furthermore, modeling 1 in 20 worst-case scenarios reveals that all US personas suffer larger nominal shocks than UK personas.
To do sensitivity analysis on the model, we applied plus or minus 10% variation independently to each of the parameters and plotted the 5 most impactful ones in terms of disposable income. The figure on the right shows that our model is highly stable as it displays perfectly symmetric and linear responses. The figure on the left is the result of the model not allowing negative disposable incomes. To do stress testing on the model, we use 50% variation instead. The figure on the right shows that this breaks the symmetry as personas enter higher tax brackets. So why is this model strong? First, it's mechanistic and extensible, as it's built on modular logic rather than curve-fitting data. Next is high in granularity. For example, the model can capture seasonal variations as it tracks disposable income monthly instead of annually. Finally, we embrace real-world unpredictability by using results from a Monte Carlo simulation instead of a simple and fragile average.
Moving on to question 2. So the aim here is to model gambling behavior evolving over time rather than treating gambling losses as a fixed number. So we track 4 things here. We track risk tolerance, wealth, profit, and session behavior, which we will elaborate. We built a model with a baseline demographic risk, so your background, dynamic bet selection and stake sizing, so your previous decisions will impact your upcoming decisions as well. A win-loss feedback through loss chasing, and taking all of this into account, we decided that an agent-based Markov state automaton will best provide accurate and efficient results. So as a model overview, just to kind of show what the model does before, as I say, we elaborate, we initialize the automaton, we decide on the bet, we place the bet, we decide to quit or continue, and then we calculate the total profits. So that's kind of the broad kind of engine behind this model.
So we decided to use the fact that risk-taking decreases with age, and also that men are more have a higher risk appetite than women. And this was taken from these studies and also from the bot data that Julia will expand on, and we use these as base parameters for our simulation.
So we made 3 key design choices. Firstly, we decided to use a Markov automaton because human behavior is not deterministic. It's much more stochastic. And for this reason, so that we could get an aggregate result, we decided to use multiple agents so that we can get a mean result for one demographic. And fundamentally, our model is a psychological model because gambling behavior is not based on rational behavior, but on psychological factors such as risk appetite. So our model starts by, first of all, calculating the base risk tolerance for a given agent, and this happens by taking the demographic data on the left with the bar column, and we fitted curves to that data to obtain the base risk tolerance. Then we initialize our Markov automaton with the previously calculated risk tolerance, and we assign some initial wealth to them as well. Then the agent starts placing bets. First, it selects which risk profile fits its current risk tolerance, and it does so by including an income factor as well, which means that the higher the income, the more risk an individual is willing to take. We also impose a minimum and a maximum stake that the agent has to wager per bet. Then we actually calculate the results of the bet, from which we obtain a profit for the bet, and also an updated risk tolerance based on whether the model loses. And in that case, we multiply the previous risk tolerance by chasing coefficient. Then we update the wealth of the agent by the profit, and we also update the wealth monthly by some fixed amount. Finally, a betting session terminates on 3 conditions. 1, if the agent runs out of money to bet. 2nd, if the total losses surpass the maximum stake they're willing to wager. And 3rd, if they just randomly decide to stop gambling due to a risk tolerance. And this is looped over multiple sessions, multiple months, and multiple agents. And then it's aggregated, and we take an average over multiple agents to obtain the final profits from the gambling annually. And so here's another summary of our pipeline.
As for the results, we firstly find that youth correlates with financial losses. More specifically, we uncovered the extreme risk appetite of younger males, which is what contributes to their steep early losses. Finally, falling into tilted behavior, that is to say chasing losses, drastically accelerates financial ruin.
We also find that strict limits prevent financial ruin. The distribution of bettors with strict limits in orange are skewed further to the right, showing lower losses with a lower spread. On the other hand, those with mental accounting experience bigger losses, with the distribution being skewed to the left, and also a much bigger lower tail, showing the worst case scenarios result in much bigger losses. We also find that absolute losses scale with wealth. However, these act as a flat tax across incomes.
To do sensitivity and scenario analysis on the model, we used lower and upper bound values for the four most important variables and plotted the change in average annual net profit. The figure shows that our simulation avoids single-factor dominance, confirming our choice of the most critical variables. The figure also shows the simulation remains strictly bounded. Furthermore, we applied the behavioral stress test to the chasing coefficient, changing the behavior from risk chasing to risk averse. This shows that the model accurately models psychological profiles without breaking.
Now, moving on to question 3. Question 3 asks what happens after the gambling loss has already occurred. So the focus is not just the amount, but the long-run damage financially. So just introducing the question, what I said, the RBM, as computer scientists, we have a tendency to quantify everything. So we decided that a recovery burden months model would be most appropriate, which, as the slide says, measures how many months of ordinary saving are needed to repair the harm. We have 3 compartments which we will elaborate: depleted savings, missed investment growth, and debt accumulation.
So we assume a typical low-risk fund returns 7%, average credit card APR is 22%, average gambling loss is $200 per month, impulse spending is $50 per month, and monthly saving is $500 per month, all taken from these studies.
So in terms of the actual structure of the question, so first of all, we compute the harmful shortfall. Then we convert the annual rates to monthly rates. We solve the 3-gap ODE system with MATLAB ODE 45, and then extract final gaps and turn them into RBM. So this is the actual execution. At the top, RBM is calculated as the total repair deficit divided by the monthly saving capacity. So the numerator is the financial damage that needs to be repaired, the total financial damage, and the denominator is how much the person can realistically save each month. Before calculating the damage, we first determine the harmful shortfall, which is kind of the cushion for the person's safe monthly costs. And then the 3 compartments I was talking about, which are depleted savings, missed investment growth, and debt accumulation. And then we have our monthly rates and initial conditions. At the bottom, we convert annual rates into monthly rates, and we also can't forget that we start the damage compartments at 0, which means we consider additional damage caused by the gambling event. So that the model doesn't really ask how much do they lose, but how much future financial recovery has that loss created.
And so we use the built-in ODE 45 solver, which uses the Runge-Kutter method for the 4th and 5th order. And that means that it can determine a loss in accuracy and change the step size accordingly. As we can see on this example graph, for turning points and points of inflection, it took many more samples to remain accurate. And we use this ODE solver as shown in our code.
We found a few insights on gambling impact. First of all, debt-funded gambling creates an exponential recovery timeline. Secondly, budgeting a financial buffer offers a false sense of security, meaning unexpected expenses can quickly increase the number of recovery burden months. To do sensitivity analysis, we applied plus or minus 20% variation to each of the parameters and plotted the top 7 most impactful variables. The figure shows that the model is insensitive to interest rate errors. It also shows that recovery is overwhelmingly dictated by direct monthly cash flows rather than interest rates. As for our findings, firstly, vulnerability exists before gambling begins. Financially fragile households are already closer to deficit. Secondly, gambling harm is amplified by behavioral feedback. Finally, debt-funded losses create much worse recovery paths than reduced savings alone. Overall, we found that gambling harm is uneven, self-enforcing, and long-lasting.
So circling back to our theme on technical computing, I'll just quickly talk on how that helped our model overall and our structured approach to the question. Stochastic simulation using the methods described. Of course, as humans, we can't really pinpoint randomness. So as I say, the methods described allowed us to do so. The dynamic state updates, more specifically with question 2, with a Markov state automaton, we can as I reiterate, our previous decisions impact and influence our upcoming decisions, and of course your current background and other details. The numerical OD solving that Jula spoke about in MATLAB to, of course, help us get more accurate results. And then the sensitivity analysis, so the key drivers behind the results we got, whether that be risk tolerance, loss chasing, the stake size, stopping rules, or income and bankroll. So overall, technical computing just made our lives so much easier. Thank you very much for listening.
Yeah, go for it.
Can you show me the differential equations you all use ODE 45? I missed that one really quickly. What was it?
This one?
Where is it?
Is this the one you were talking about?
Yeah, where's it? Oh, there it is. No, where is the final ODE? Oh, you had a system there. Okay, good. Thank you. I have an actual question.
Yeah, go for it, yeah.
All right, okay. So what would you do in your model, I think specifically maybe question 2, if you had like big events, right? Big betting events like the Super Bowl or the World Cup and things. How would you change that, or how would you incorporate those features?
Well, one thing we would do is we would change the model to become much more fine-tuned psychologically. So at the moment, we only keep track of risk tolerance as a possible psychological factor, but we could perhaps use other psychological metrics. At the moment, we use the BART risk metric, which means that someone pumps some amount of air into a balloon, and if the balloon pops, they receive no amount of money. If the balloon reaches a larger size, they receive more money. But this isn't a one-to-one with the betting we use, because here they lose all their previous money. And perhaps we could incorporate other types of risk aversions and like break it down into different psychological factors instead of just aggregate it all into one risk tolerance.
So I'm looking at, I'm not sure what, where the psychology piece comes in, but I'm looking for the events that have, big bets going on, right? Like Super Bowl and World Cup. Maybe am I misunderstanding?
Yeah, could you elaborate on the question?
Well, I think those events are an opportunity for people just to take, I guess, big swings, and there's lots of opportunity around betting then. So does that get incorporated, or would that get incorporated in a new version of the model?
That's part of
Or
our
is that-
model. Yeah, that's already part of our model.
All right, okay.
I have a question about problem 1, which is a question that could apply to a lot of our teams. So like many teams, you observe that disposable income can be negative sometimes. And this can mean some things. It can mean you take on credit card debt. It can mean you don't take on debt at all if you had savings from previous years. And we haven't seen that many teams think about what happens across years. So I wanted to ask if you guys had thought about that. Like if I have negative disposable income in 1 year, does that mean I don't bet at all? If I have positive disposable income in another year, does that mean everything I don't bet goes into savings? Like, how do we account for the fact that money transfers across years?
Actually, I think we accounted for that mostly in question 3, where we took the amount of residue and loss that's created by gambling, and then that was compounded over large spans of time. So question 1, we specifically focused on the monthly scale, but I think, yeah, that was just accounted for in a different question.
So like a quick follow-up, does your question 1 data feed into the question 3?
No, they're separate.
Would that be possible to do?
It would be possible, yes. In fact, we could, as discussed earlier, we could link all of the questions in one big model where the first question determines the salary, which is part of what determines the wealth in question 2, and then question 2 provides the data for the Q variable we showed in question 3. So they could all be linked together.
Okay, sounds good. Thank you.
Yes, I do have one more question. So first, I'm very impressed with all the coding. I am not a computer scientist, so I am impressed. It looks like you have a lot of steps, a lot of variables, a lot of stages, and, well, mathematical modeling. Was there a stage where you thought, wait, it's going too much, it's too complicated? could we step back? How did you make that decision? Or probably not. Probably you were just developing more and more details.
Well, it was a 14-hour time limit.
Exactly.
So what we decided was we sort of, well, first we tried to get a general idea of what we would answer for each question, and then we just took them in turn. And if we thought we were overstepping, we would try and work on another question and come back. Like, there were some details which we missed for question 1, but like in terms of
I'm
like
sorry,
taxation.
What kind of details
Like,
you think you missed?
So,
Sorry.
yeah.
May I answer that about why you missed something we missed about question 1? So one thing we assumed was that the variables are independent, so we don't directly hard code or model any dependencies between the variables. And this was a deliberate choice to keep it computationally tractable. And also, in the 14-hour time frame, it was hard to find any covariance data. So any dependence relationships that we will be modeling will be based on our own guesses. So that means the model would only fit those guesses, fit scenarios that fit those guesses, rather than be generalizable.
Well, sometimes you have to make those assumptions to simplify, to make actually model possible. Right. Thank you.
Okay, thanks so much, guys. That wraps us for questions. You have a minute to say any thank yous of your own if you would like to.
Okay, thank you. So first of all, I want to say thank you to my teammates. We participated last year and we've taken on so much things we've learned from last year, and obviously here we are. Thank you to the judges very much. Thank you to Siam, M3, for all the organization. We loved New York, and Jane Street for the venue, of course. And finally, Mr. Loxley for his support before the competition and critiquing our model from last year to make sure that this year is kind of not perfect, but approaching perfect. But thank you very much.
Thank you.